Alright guys, hello and welcome to today's lesson. This is Mr. Ludden and today we're going to have a look at indices. These came up in my functions video when we had a look at exponential functions, and today we're going to have a more careful look at them, at the numbers involved, and we'll see how they come up in an actual exam type question as well. Any of the notes that I write down in this PowerPoint in this video, I will have them in the description as well, so you can copy and paste them into your own notes. I also put in a link to the functions video that I did in case you want to go back and have a look at that. Other than that, I'm going to jump straight in, and where you would have seen indices before is when you looked at bird mass in first year. You may have also done it in 6th class, and the I there is your indices. Just in case you didn't learn it as bird mass, in case you learned it as BOMDAS or BIMDAS or BIDMAS, they all mean the same thing. There's literally no difference in between them. The R there stands for roots, and that's a relatively new one that they've put in, but as we'll see in a couple of minutes time, the roots here very much link into our indices. So we'll have a look at those two things are heavily related. So we'll be having a look at those in a minute or two. And the indices that you would have had a look at would have looked something like this. So you would have said like 2 squared, and you would have learned that that was 2 times 2, which is 4. And maybe you might have had a look at 2 cubed, 2 to the power of 3, and that was 2 times 2 times 2, which is 8. And then you might have said, well, 2 to the power of 4, which is 2 times 2 times 2 times 2, which is 16. And what you would have learned is, well, writing 2 to the power of 4, I'll just get my highlighter, writing 2 to the power of 4, well, I've only written down 2 numbers there, but I represent all of these 4 numbers here. So writing 2 to the power of 4 was a more efficient way of writing 2 times 2 times 2 times 2. And you might say, oh, well, I prefer writing 2 times 2 times 2 times 2, and that's fine. But if you get something like 2 to the power of 20, all of a sudden, like, it becomes really apparent. 2 to the power of 20 is a whole lot easier to write than 2 times 2 times 2 20 times. So it's, in summary, writing something with indices is a more efficient way, a better way of writing loads and loads of multiplication. Now, just to refresh your memory on just some vocabulary, just so you know what numbers that I'm talking about in the rest of the video. In the number 2 to the power of 20 here, the number 2 is called your base, and that's going to be the big number at the bottom. That's going to be the number that you're multiplying by itself a whole load of times. And the 20 here is called either your power or your exponent. Usually called your exponent. This whole thing altogether is 2 to the power of 20. But if I say in the next couple of minutes, if I say the word exponent, you know that it's the number up here in the power part of your whole indice. Okay, so we're going to have a closer look at the numbers here, I suppose now, the 4, 8, 16, and so on and so forth. And we're going to try and see if there's any rules that we can come up with by looking at the patterns involved in those numbers. And then we're going to see if they match up with what's in the log tables. Okay, so I've done a table here with 2 to the power of certain numbers. So 2 to the power of 3, I'm going to just do some rough work over here. And 2 to the power of 3 is 2 times 2 times 2, and my answer there is going to be 8. 2 to the power of 2 is going to be 2 times 2, which is 4. And those were 2 of the ones that we had a look at just like literally a minute ago when we were over here, like our 2 squared and our 2 cubed. But what I want to have a look at is what happens when my exponent starts getting smaller and smaller. So if you'll notice, just in case you weren't aware, I put my exponent starting at 3 and going down to 2, 1, 0, and then minus 1, minus 2, and minus 3. And what I would like you to do now, just to get the whole benefit of this video, is pause the video and see, can you visualize what's going to happen here, 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 and here. Is there going to be a pattern? Can you spot any similarities between the numbers? Anything interesting at all? Anything unusual? So I'll get you to pause the video now, and I'm going to start again in 2 seconds. All right. Okay. If you had paused it, you would have come up with a couple of numbers in this column here, and we're going to have a look at those now. 2 to the power 1, if I put that into my calculator, I'm going to get 2 as my answer. And sometimes people get a bit tripped up on that one there. But if you think about it, 2 to the power 1 means I'm multiplying 2 by itself just one time. So 2 multiplied by itself one time is just going to give you 2. The same thing if you had 3 to the power of 1. 3 to the power 1 is going to give you 3. If you had like a million to the power of 1, that would be a million. So the first rule that we're going to come across, and this rule is going to be in our log tables, and I'm going to put that just up here, is that anything, so I'm going to represent that with a, anything to the power of 1 is the same thing as that number. So a to the power of 1 is equal to a. Now the next one we're going to have a look at is 2 to the power of 0. And when I put this to my class, whenever I'm explaining this, or when we're on indices in the actual classroom, I say, without calculators, have a guess, what would 2 to the power of 0 be? And I get a range of answers. I get 2, I get 1, and I get 0. They're the most popular answers. If you put 2 to the power of 0 into your calculator, if you put that in, 2 to the power of 0, you will get 1 as your answer. And the way I'm going to describe that, the way I'm going to explain why that happens, is with the 3 numbers above it. So 2 to the power of 0 is 1, so I'm going to put that in there. And we're going to see if that fits the pattern that's happening with the 3 numbers directly above it, as I said. So we've got 8, we've got 4, we've got 2, and we've got 1. So if you think about it, if I was to get from 8 to 4, well, what would I do? What would I divide it by? And we should be able to see that 8 divided by 2 will give you 4. How would I get from 4 to 2? Well, I'm going to divide by 2 again. And this pattern continues all the way down. If our indices goes down in steps, so like 3, 2, 1, 0, minus 1, minus 2, minus 3, I'm going to be dividing by 2 each and every time. So what we're going to end up with now, especially like this brings us on to our negative indices, 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3, which some people get tripped up on as well. If you think about it as just dividing by 2, we'll have a look at what happens. So 1 divided by 2 will bring me to my next line here, divided by 2, and that's going to be a half. A half divided by 2, if you think about it, if you were to break a half into 2 equal parts, we would end up with a quarter. And a quarter divided by 2 is going to give you 1/8. So if you had paused the video when I'd asked you to, and if you had gotten those ones, well, without a calculator, well done. The 2 to the power of 0 and 2 to the power of negative numbers are the ones that people get mixed up with the most. So if you can see the pattern that's happening there, this will make our job a whole lot easier when we have a look at our log tables. Speaking of log tables, there's a couple of more rules that we can sort of pull out of this table to see what's happening. And in order to do that, I'm just going to take away my rough work here at the side, my divided by 2. Just going to take away all of those so that I have a bit more room here to show you what's going on. And we're going to have a look at 2 to the power of 0 first. So 2 to the power of 0 here is equal to 1. The same thing, you will get the same answer for 2 to the power of 0 as 3 to the power of 0 or 4 to the power of 0 or any number to the power of 0. If you don't believe me, you can check on your calculator, pick any number you want. I'm going to pick 25. If you put it to the power of 0, you will get 1. If you have 17 million 357 1 2 3 to the power of 0, your answer will always be 1. So if you have any number to the power of 0, your answer will always be 1. And again, you can check that on a calculator, pick any number you want, put it to the power of 0, and you will get 1. So right now, even without looking at any log tables, we have 2 of our laws of indices right there. The next we're going to have a look at is the link between 2 to the power 1 and 2 to the power of minus 1. And I'm just going to get rid of my highlighted stuff here so that I can show you exactly what I'm talking about. Okay, so we've got 2 to the power of 1, and we're going to compare that to 2 to the power of minus 1. You'll notice that 2 to the power of 1, if I change the sign there of the exponent, so if I change the 1 to a minus 1, well, my 2 is inverted. So to invert a fraction is to sort of swap it around, swap the numerator with the denominator. So if you think about 2 as a fraction, that's 2 all over 1. So to go from 2 to the power 1 to 2 to the power minus 1, like we'd change the signs of the exponent. What that does to the actual fraction is it gives you the inverse of that fraction. In your log tables, what that looks like is if you have a to the power of minus n, so a to the power of minus n, in our question over here, that would be 2 to the power of minus 1. That's the same thing as 1 all over a to the power of positive n. So in our question over here, it was 2 to the power of 1, which is, as we saw before, 2 to the power of 1. Where have we seen that before? In our first rule of indices that we had to look at, this one up here. Anything to the power of 1 is that number, so is equal to a half. So that's a handy one to have, because it helps you get rid of negative exponents, and it can also help you get rid of fractions depending on whatever the question is asking you. And we'll have a look at those in a minute or two. Okay, the last 2 things I want to have a look at will take me this page here, and you might be asked as like an A part of a question in the exam. So the first part of your question, you might be asked to simplify, let's say 2 to the power of 15 all over 2 to the power of 7. And actually I'm going to pick a lower number here, 2 to the power of 8, let's say. It'll help me out when I'm showing you how this question is done. So you might be asked to simplify that, and you could, like, I suppose you could put that into your calculator, I suppose, but just to show you exactly what's going on here, 2 to the power of 8 is 2 times 2 times 2 times 2 times 2, 5 of them, 6, 7, 8, and 2 to the power of 7 is 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7. That's what your question looks like when you expand everything out. And it sort of goes back to my previous point. 2 to the power of 8 all over 2 to the power of 7 is a whole lot easier than writing what I just went through there. Now you'd be asked to simplify that. Now if you think about it, if you divided above by 2 and below by 2, so you're getting an equivalent fraction but a simpler one, what would happen is, well, all of these 2's here, if you divide it by 2, that would sort of, it would take care of the 2 at the very, very end here. So if you have 2 divided by 2, you're just going to get 1. In other words, you're going to, those two 2's are going to work against each other. A lot of people say cancel out. I don't like the word cancel out, because when we're looking at fractions, in the future, I find people do mad things. They go cancelling crazy things. So I don't use the words cancelling out. I'm going to say work against each other here in order, and it gives us a simpler fraction all in all. You'll notice that up on top here, there's a whole load of more 2's, and at the bottom there's a whole load of more 2's. So I'm going to see if there's any more sets of 2's that work against each other. This 2 and this 2 will work against each other. This 2 and this 2. This 2 and this 2. This 2 and this 2. This one and this one, and finally this one and this one, and we ran out of 2's that can work against each other. So what we're left with is 2. So 2 to the power of 8 all over 2 to the power 7 is going to give you just this 2 here on its own, because everything else has worked against each other, and your 2 here is your most simple answer. If we remember back to our the laws of indices that we had to look at, and especially this one here, a to the power of 1 is a. I'm going to use that to give this 2 here its full name. This is actually 2 to the power of 1. And if we look at the exponents in each part of this question, we've got an 8, a 7, and a 1. So you might be able to see a relationship here between 8, 7, and 1. Well, if I take 7 away from 8, I'm going to get that 1 here. So in our log tables, that rule right there is written down as a to the power of, I'm just going to quickly check my log tables, AP and AQ, just AP and AQ is equal to A P minus Q. So if you have some number to the power of a number divided by the same number to the power of another number, you can simplify that to whatever your base number actually was and then take away the powers. So if I had, let's say, 2 to the power of 23 and 2 to the power of 17, if I was to apply this rule here to that question, I could say that that's the same thing as 2 to the power of 23 minus 17, which is 2 to the power of 6, which is a whole lot easier than writing out all the stuff that I've done up here on top. So when we are dividing indices, we are taking away the exponents. And just be careful of the position there. The P or the Q is being taken away from the P, not the other way around. So just be careful of that. Alright, last one we're going to have a look at, then we'll have a look at the log tables. I'm just going to take this part here away. Is multiplication. So let's say we've got 2 squared multiplied by 2 cubed. 2 squared is the same as 2 times 2, and we are multiplying it by 2 cubed. So that's the same thing as 2 times 2 times 2. Now I'm just going to get my highlighter. So my 2 squared is that 2 times 2, and I'm going to get a different color here. Let's go orange. 2 cubed is that 2 times 2 times 2. So I've just written those out fully, and then the multiplication sign in the middle, that bit there and that bit there. Well, that was there in the question at the start, so I still have to bring that with me. So if we were to do that, 2 times 2 times 2 times 2 times 2 is going to give us 32. Is equal to 32. Oh, not 3 to the power 2, excuse me. That's going to give me 32. If I was to write that as like 2 to the power of something, you will find out that 32 is the same thing as 2 to the power of 5. So 2 times 2 times 2 times 2 times 2. So if we took our answer here and just put it straight at the end of my original question, I would have 2 squared times 2 to the power of 3 is equal to 2 to the power of 5. And what we're going to have a look at is there any relationship between the two, or the exponents here, the 2, the 3, and the 5. And you should be able to see that 2 plus 3 will give you 5. Now how that's written in your laws of indices is as follows. You'll have a to the power of p multiplied by a to the power of q. Oh, q. And that's the same thing as saying a to the power of p plus q. So if you have two indices being multiplied by each other, and the base numbers are the same. A quick way of doing that is adding the exponents together. All right, I've done an awful lot of rough work, and we've looked at 4 of our laws of indices. What they look like in your log tables are as follows. On page 21, you have all of this going on. But for your junior cert, you only need 1 column of those. So what we're going to have a look at today is nearly everything in this column here. That's on page 21 in your log tables. You do not have to learn everything that we've done so far, like everything here, 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 but you do need to be able to recognize them. So the more practice you do on these, the better you'll be able to recognize them, and then your log tables can just be used for reference or just to make sure that you're doing things correctly. The column that I'm after highlighting there is, as I said, it's what we'll be having a look at, and I'm just going to get rid of what's over here. I'm just going to put my line through those because logs, like where your log table, like the name of your log table actually comes from, is like you can see the word log written all the way over there. We don't have a look at those until our leave insert, so we're not going to have a look at those now. If you remember just back like 30 seconds ago, we had a look at this rule here. We had a look at this rule here. We had a look at our 4th one. We had a look at this one. And there's a couple more there. I could go through them all, but then this video would be like an hour long. The ones that we had a look at are the most important ones to be able to identify. And for most of your questions, they'll get you out of a lot of trouble. We will have a look at all of those today though, especially the ones that are applied to our exam question in a couple of minutes. Just before we have a look at our exam question, there's just one of these more that I want to just highlight to you, and I'm going to use a little bit of rough work here. If you've seen the square root of a number before, so like the square root of 9, let's say, you would have said that like the answer to this, you could put it in a calculator and you get 3. But what you're looking at is like what number, when you multiply it by itself will give you the 9 here. So the square root of 9 is 3. Now you mightn't have been told that the full name for that, the square root of 9, is that symbol there, so the square root symbol, but with a little 2 here. The 2 is never written in your maths books when you're looking for the square root, but that right there is the full name of it. And it ties into this law of indices here. So the square root of 9 is 3. Like my answer isn't going to change. I've just given this its full name. If you were to write 9 to the power of something, and you wanted it to mean the same thing as the square root of 9, you would be writing 9 to the power of a half. So 9 to the power of a half is the same thing as the square root of 9, and we need to be aware of that. In your log tables over here, a to the power of 1 over q is equal to a to the root of q. That's the way it's said. And I'm just going to take this part away. That was just an example. Just what you need to know is that if you have the square root of a, that's the same thing as a to the power of a half. So that might get you out of trouble in one of your questions. If you see a square root, it's to the power of a half. Okay, we've spent nearly 25 minutes looking at where everything comes from there. I'm going to get rid of this and that over there and this. There we go. And what we're going to have a look at is an exam type question. So in 2016, question 9 looked like this, and there was also a B and a C part as well, all to do with indices. Over on this side here, I've written out, or I've copied and pasted even, my log tables, just so I have them. And what we're going to have a look at is how to use what's in our log tables to help us answer each one of these questions. Okay, if we have a look at the actual question here, it says write each of the following numbers in the form 3 to the power of k, where k is an element of q. Okay, so the first thing we're going to just be sure of is that for our answers here, we need to find out, well, 9 is equal to 3 to the power of something. What is that something? 1 is equal to 3 to the power of something. What is that something? Root 27 is equal to 3 to the power of something. What is that something? And the same thing for your last question down at the bottom there. Your k up at the top, so your exponent has to be a quotient, so it has to be written as a fraction. So your quotient numbers can be written as a fraction, so like a half, a third, 4/7, any fraction you want. It can also be a whole number, so let's just bear that in mind. Okay, our first one, fairly straightforward. We want to write 9 as 3 to the power of something. So I suppose our three, not our 3 times tables, but our multiples of 3, not even our multiples of 3, 3 multiplied by 3, our powers of 3 come into play here. And we have to find out, well, 3 to the power of what will give me 9. So we should be able to see that 3 squared is 3 times 3, and that'll give me 9. And that's our first question done. So that was just recognizing that 3 squared was equal to 9. So they're easing you into the question here. Second one, a small bit trickier. 1. We want 3 to the power of something to be 1. And if we have a look over at our laws of indices here, we know that anything to the power of 0 is 1. We know that. So if we apply that to this question here, 3 to the power of 0 is going to give me 1. So 3 to the power of 0 is my answer to the second part of my question there. Our third question, a small bit more tricky, and we need to go back to our actual question here. They want to write each of the following numbers in the form 3 to the power of k. But for our third part of my question here, the 27, that's not like 3 to the power of something just yet. So what we need to do is we need to write our 27 as 3 to the power of something first, and then we'll worry about our square root on that. So 27, if you think about it, 3 times 3 times 3 will give you 27. And that's the same thing as 3 cubed, so 3 to the power of 3. So what I'm going to do is I'm going to write my root 27 as square root of 3 cubed. And now we're nearly there. We have our 3 cubed, but we have the square root on it as well. So what I need to do is get rid of my square root here, because there is no square root in the way that they want their answer up top here. So as I said a couple of minutes ago, the square root means to the power of a half, and in this case it's going to be 3 cubed and everything to the power of a half. Now we're nearly there, but we have to deal with this part here, the 3 and the half. So I'm going to go over to my log tables now, and I'm going to see which one of my log tables rules will help me in that situation. And if I go down to my third one, you'll notice that we have the exact same scenario here, where we've got 3 to the power of 3 all to the power of a half. And in this one over here, and I'll just this one here, my a is my 3, the base 3, my p is my exponent 3, and then my q is my other exponent, a half here. And it tells us that if we have a scenario like this, we can rewrite that as a and then pq together, so p multiplied by q. So what that'll look like is as follows. It'll be the same as 3 cubed times a half. So I know that's not the, let me do that again. Okay, so we've got our base 3, and then our 3 up top here, and then our half. So it tells us up here that PQ, that means p multiplied by q. So in the same scenario here, I'm going to have 3 multiplied by half, which will give me 3, my base 3, and then this bit up here, 3 times a half will give me 3 all over 2. And if you put it into your calculator, root 27, it might give you 3 to the power of 3 over 2 if you have your calculator on, if your calculator works with powers like this. I know it's either the Sharp or the Casio ones that don't, but I just need to be sure that, I suppose. Sometimes your calculator won't go all the way and give you your 3 to the power of 3 over 2. And in order to get your marks in the exam, you need to be able to show your workings out to do that. So 3 to the power of 3 over 2 is your answer for the third one there. Remember, 3 over 2, it is an element of Q. It is a fraction, so you're good there. Alright, for my last question here, the fourth one, I'm just going to need a small bit more room to show you what's going on. So I'm just going to move my previous answer, my 3 to the power of 3 over 2, 3 to the power of 3 over 2. I'm just going to move that over there. If you need any of the working out here, I'd advise you to pause the video now and take that down, because I'm going to take those away. Alright, draw, and there we go. Okay, for this question here, 1 all over the cubed root of 3. Remember, we want our answer as 3 to the power of k. So what I'm going to do is I'm going to try and rewrite everything here, my numerator and my denominator, as 3 to the power of something. The first one I'm going to write deal with is the 1. And we know that 3 to the power of 0 will give me 1. So that's equal to 1. And I know that down here at the bottom, the cubed root of 3, if I use, I'll just get my highlighter, and I'm just going to get rid of that last bit that I used. If I use this law of indices here, on my right hand side I have a to the root of q, and that's exactly what I have at the bottom here, and I have 2 3's. So if I was to work backwards now, so I'm working from like this part here to this part here, and if I was to change the cubed root of 3 to 3 to the power of something, what I would end up with is, and I'll just write this out fully, 3, the cubed root of 3 is going to be 3 to the power of 1 over q, and my q here was my 3, so it's going to be the same thing as 3 to the power of a third. So that one there we hadn't have a look at, but the way you substitute in the numbers that you're given, it's the exact same way as what we've done before, but I haven't gone explicitly through how that works. But as long as you're comfortable with like how the first couple work, the other ones follow the same pattern. Sometimes they can get a small bit more complicated, but if you can just keep your head screwed on, I think that's the biggest thing to do. Take everything step by step. So you'll notice with this question down here, question 4, I'm taking the numerator first, and then I'm taking the denominator. I'm not taking all the fraction as a whole, because I'm going to end up in a lot of trouble. So back to what I was saying, the cube root of 3 is 3 to the power of a third, so I'm just going to take that away, and I'm going to put that here, 3 to the power of a third. So right now, what I've got here means the exact same thing as what I have over here. And I just have one more step to go. You'll notice that I have 3 to the power of 0. Now, I don't like to look at this here. Hopefully I can write it better now. There, that's a bit better. I have 3 to the power of 0 all over 3 to the power of a third. If you have a look at our second law of indices over here, it gives me this exact same scenario. So this right here is the exact same thing as saying 3 to the power of p minus q. Now p was the exponent at the top. That's going to be my 0. take away my exponent at the bottom, the q, which is a third. So if I tidy that up one last time, I'm going to end up with 3 to the power of 0 minus a third is just minus a third. And if you put that into your calculator, if you put this into your calculator, it means the exact same thing as this over here. So again, the advice that I give to you is just take it step by step. Your log tables are there to help you. Just be totally sure on what you're actually doing. Take it step by step. Don't rush into anything mad. There will be something here in the log tables that'll help you. If you're using division, if there's a division sign in your question, chances are you'll be using this one. If you're multiplying two things together, chances are you'll be using this one. If you have something to the power of 0, chances are you can use the fact that a to the power of 0 is 1, and so on and so forth. Your hardest part will be to apologies about that. Your hardest part will be to pick what laws of indices to use and to use them correctly. Be careful which number is your base, be careful which number is your exponent. Alright, the rest of your question, and this was just using your laws of indices, and then the rest of the question asked, well, what's the story here? So your B part, write minus 2n to the power of 4 in the form a, n, b, where a, b are an element of z. So what that means is they want to find out what a is, find out what b is, where a and b are elements of z, where a and b are integers. So your integers, if you remember, they are your positive and your negative whole numbers. So that's like your terms and conditions in this question. Let's see if we can do this. Minus 2n inside the brackets here, that's minus 2 multiplied by n. So if we have a look at our first law of indices here, I'm going to apply this law to what's going on here. So my next line is going to be, well, that's the same thing as minus 2 to the power of 4 times n to the power of 4. I've just used my first law of indices there. On closer inspection, I've jumped straight into that question and I've done exactly what I told you not to do. You'll notice that applying this, my first law of indices here, I haven't done what that law says, and on a closer look, that law there is not going to help me. So I'm just going to start that question again. My answer is right here, but I haven't pointed you in the direction of the right law of indices to use. So what we have here is some number multiplied by another, and it's in brackets, and then it's also the power of something else. If we look way down our list here, this here is the law of indices that we need to use, because we've got the exact same scenario. We've got some number multiplied by another. So in this case, my a here is going to be my minus 2, my b here is going to be my n, and my p here is going to be my 4 up top. So you saw how I jumped straight into that question, and I would have made a mess of it if I continued on. Just be careful that the question that you're starting off with, it looks exactly like the law of indices that you're going to use, because my one looked similar, but it didn't apply to the question that was at hand. So what I've done here is I've applied this rule here. So ab in brackets to the power of p is equal to a to the power of p times b to the power of p. That's what I've done here. At this point here, that was the hardest thing to do about that question, identifying what law to use. Right now, all you have to do is find out what minus 2 to the power of 4 is. Minus 2 to the power of 4 is going to be minus 2 times minus 2 times minus 2 times minus 2. You can put that into a calculator if you want. If you are putting that into a calculator, just be careful that you put your brackets around the minus 2, because otherwise your calculator might give you a different answer. So when you do that, you should get 16. And n to the power of 4, a better way right now is n to the power of 4. So if you look at what you have now, you've written it as a to the power of n, or a n to the power of b, where your a is 16, your n is just your n, and your b is 4. So you've done that question where a and b are elements of z. Are a and b integers? Are 16 and 4, are they integers? Of course they are. they're positive whole numbers. If they were negative whole numbers, they would have worked as well, because your z's here, that takes into account your negative whole numbers as well. So just finishing off that question, I'll just make doubly sure. Just be 100% about which law of indices you're using there. Yeah. Alright, for your C part, it asks you, well, it asks you a question like not sort of to do with your laws of indices, but more like, do you understand what's going on? And it says x and the square root of x squared are not always equal, and asks you to give an example of a value for x and the corresponding value of the square root of x squared, which are not equal. So you might think, well, if we had a look at this here, like squaring something and then getting the square root of it, they're opposite results. So let's say if I put in, let's say if x was 3, let's say x was 3, and I'll just walk through this just so we can see what's happening, so we have a better idea when we're dealing with x. Well, 3 squared, that's the same thing as 9, because 3 squared is 9, and the square root of 9 is going to give you 3. Now this 3 here is the exact same as the 3 we started off with, but in the question they've told us that x and the square root of x squared are not always equal. Well, in this case they are, so we're in a bit of trouble. We have to find out a number that we can put in here, and so that we get a different number out. Now if you think about this, if you put in positive numbers, so if you put in, let's say if we put in 4 in here, 4 squared is going to give you 16, and the square root of 16 is going to give you 4. So that 4 there is going to be the exact same thing as that 4 there, which doesn't really help us. If you put in any positive numbers, that's what's going to happen. So what we need to think is, well, what's the opposite of a positive number? Can I put in any other kind? And what we're going to do is we're going to put in a negative number, and we're going to see what happens. So into this here, we're going to put in a negative number. I'm going to put in, let's go -1. So the square root of -1 squared. Now, if we look just inside the square root here, -1 squared, that's the same thing as -1 times -1. So -1 squared is -1 times -1. Now a minus times a minus will give you a plus, so that's just going to give you a +1. So that's just my rough work over there. I'm going to need that space in a minute, so I'm going to rub that out. -1 squared is going to give you 1, and you still have the square root there. So the square root of 1, if you think about it, is 1. So right now we have an example of where we started off with a -1. We put in -1 for x, so down here x is -1, and we got that the square root of x squared was +1. So that's one example. In the marking scheme, if you had, let's say, -2 and 2 as your answer, that was absolutely perfect. Or any pair of a negative number here and a positive number here, that was perfect. I'm going to stick with just what I've done here, but as I said, if you had -2 and 2, if you had -10 and 10, they were just asking for one example there. Any one of those examples would have gotten you your full marks. So that one there took a small bit of thinking, and you needed to sort of think outside the box. When I looked at this question, first of all, I wasn't quite sure what they were getting at. I substituted in exactly as I'd done. There, I substituted in 3, and I said, oh, that's not going to work, and we're just going to get 3 out as my answer. Then I started looking at negative numbers. Once I started looking at negative numbers, it sort of clicked with me that if I square a negative number, I'm going to get a positive number. And once I get the square root of a positive number, that's going to be positive as well. And that was when it sort of clicked with me. So I suppose the point on that question is, if it took me, a maths teacher, a couple of minutes to get that question, it's definitely going to take you a couple of minutes as well in an exam. So don't be afraid if it's taking you a couple of minutes. Don't be afraid to substitute something in to see if something works. Don't rub out any of your workings out, because as an examiner, if you rub out something, I cannot give you the marks for it. If you put a big scribble through it, I cannot give you the marks for it. You do have plenty of pages at the back of your exam paper if you want to do a bit of working out there. If you get a question like this, and you definitely will, where it makes you think. Put down something. Just substitute in something, see what the question might look like, and you can always come back to it at the end if you have time. Just make sure you put something down for it. It's not always apparent what the answer will be, but once you start substituting in numbers or drawing a diagram or seeing what the question actually looks like, a better idea comes into your head, and it might push you towards closer towards the answer. All right. Guys, that was 2016 question 9. That was like heavily like that, and that was all your laws of indices, and then sort of testing you. Did you understand exactly what was going on? Just your key points down here at the bottom after all that. Page 21 in your log tables. That's it there. The left hand side column is really, really important. Be sure which number is the base and which is the exponent, because that'll help you when you're applying your laws of indices. Read the question to determine which law of indices is best to use. So if you have a division sign, or sorry, a fraction in your question, make sure you're taking away the powers, etc., etc. And the 3 here that'll help you out, I suppose, just straight off the bat, is that a to the power of 0 is 1, a to the power of 1 is a, and a to the power of a half is the square root of a. And I'll just put the little hat on there. Guys, as always, I'll put the key points in the description. If there's anything I've forgotten, I'll put it in the description as well. And yeah, that's the main things on indices. Thanks for listening.